Talk about a review from pre-calculus of finding the domain of a function. Here I'm actually going to talk about finding the implied domain. Remember, the domain is just the set of all inputs to a function, whereas the range is the set of all outputs. So when we ask what's the domain of the function, it may be that the domain is given explicitly. Okay, in that case, you could say, maybe I have a function f of x is equal to x squared, but then after it I'll say, comma, x is greater than or equal to 0. So the domain of the function x squared is actually, in general, if we asked what the implied domain was, that would be any real number, okay, the set of all real number inputs to the function for which there's a real number output. So if I just had x squared, that domain would be all real numbers because I can simply square any real number and I always get a real number output. But by doing that, that's an explicit domain saying I'm only going to consider values of x greater than or equal to 0. This happens a lot of times when you're looking at an application, for instance, the function's only valid for these values of the input. It could be the function is the distance an object travels as a function of time. And so you're only interested when time is, 0 or greater. Like you start the stopwatch at time 0, how long has elapsed, what's the position of the object. So that's an example of an explicit domain. So what we're interested in is what's the implied domain. So if I'm not giving you explicitly what the domain is, what is it? Well, it's just all the set of real numbers for which you get a real number output to the function. Okay, so first off, the main area is, of course, problems arise when you're dividing by 0 or taking the square root of a number. That's where you can have potential problems initially. And then there's some other restrictions with, for instance, the logarithmic functions, and then some of the trigonometric functions. So we're going to look at just a brief review of those things. So let's find the domain. This function is a polynomial function. So what's its implied domain? It's the set of all real numbers for which we get a real number output. Well, any input, I simply square it, multiply it by 3, and then add 8. If I plug any real number in for x, I'm going to get a real number output. So this domain is all real numbers. So in interval notation, the domain would be written this way. Here, what's the domain? Well, again, you have a polynomial function up top, just 3x, and a polynomial function in the denominator. So those, of course, you're always going to get a real number output for any value of x. However, we're dividing by this denominator, x squared minus 16. And we know we have a problem if we're dividing by 0. Division by 0 is undefined. It's not going to result in a real number output. So if I were to, of course, factor, in this case, the denominator, x squared minus 16 is the difference of squares, x squared minus 4 squared. So that factors as x plus 4 times x minus 4. And so we can clearly see that the domain would be any real number except when x is negative 4 or positive 4, because of those values of x would make the denominator 0, and division by 0 is undefined. It is not a real number. So how could we write the domain? You can do it in set builder notation. Curly braces denotes the set. It's the set of all values x. A vertical bar, this vertical bar means such that, or given. And then after it, what's the condition? Such that x is not equal to either positive or negative 4. So that's one way you can write the domain. If you use interval notation, you can also write it excluding negative 4 and positive 4 would be everything less than negative 4, and then everything from negative 4 to 4, and then everything from 4 to infinity. So there's the domain of this function. What about the third one? Well, now we're taking the square root of 3x minus 8. Well, 3x minus 8 for any value of x is a real number. That's fine. The problem is if I take the square root of a negative number, that's not a real number. It's an imaginary number, right? So I want to exclude any value of x that makes 3x minus 8 a negative number. That means I'm looking solely for 3x minus 8 to be not positive, but non-negative. And there's a difference. Non-negative, we include 0. In other words, 3x minus 8 could be 0 because the square root of 0 is indeed a real number, namely 0. But we solve this inequality. This is a linear inequality. So simply do what? Add 8 to both sides and then divide both sides by 3. And so the domain is all real numbers x greater than or equal to 8/3. So in interval notation, I can write that as bracket 8/3 to infinity. There's the domain for that function. Any real number greater than or equal to 8/3. Okay, let's look at some others here. This one, f of x, this time we've got x plus 4 over divided by 2 minus the square root of x. Okay, so right away I see square root of x. So right away, since I see the square root of x, I know that x has to be greater than or equal to 0. Same thing I did up here, right here. Whatever's under the radical, in this case it was 3x minus 8. Here it's just x. Whatever's under the radical must be greater than or equal to 0. But furthermore, we cannot have 2 minus the square root of x. We cannot have that equal to 0. The whole denominator being 0 would mean division by 0. And when is 2 minus the square root of x not equal to 0? Well, that's going to happen when what? X is 4. I think you can see that right away. Another way of saying this, if I add the square root of x to both sides, I cannot have 2 being equal to the square root of x. And if I square both sides, I get 4 cannot be equal to x. And so putting these two together, what's our domain? Everything greater than or equal to 0, excluding 4. So I would do bracket 0 up to 4, exclude 4, and then go from 4 to infinity for my second interval. This is everything greater than 0, greater than or equal to 0 rather, excluding 4. Okay, so again, finding the implied domain is simply find all the real numbers inputs where we get a real number output. So in these two cases, or these three cases that we looked at here, division by 0 is a problem, taking the square root of a negative number is a problem. That's the first level of finding the domain of a function. Let's look at some of our other functions. Exponential functions here. This is an exponential function, meaning the input is coming in as an exponent. And in this case, is there any value of x that would give us a problem here, make the output not a real number? In other words, can 3 be raised to any power? The answer is yes, 3 can be raised to any power. There is no restriction on the domain here. The domain is all real numbers. So in other words, I know what it means to take 3 to any, obviously, any integer power, like 3 to the 6th power would be 3 times itself 6 times. 3 to the 0 power, do I know what that is? Yeah, I know what that is. That's equal to 1. What about 3 to the negative power? What's 3 to the negative 2? We know what that is. That's 1 divided by 3 squared. That's 1/9. What about a fractional power, like 3 to the 1/2? What's that? Well, we know that's the square root of 3. So I've got everything covered. Any power I can evaluate and get a real number. So the domain is all real numbers. Now, what's the difference of the logarithmic function? So remember the inverse relationship between exponential and log functions, right? Log functions are what? What is a logarithm? It is an exponent, right? It is an exponent. In this case, when I write log x, this is really base 10. So we usually don't write the 10 down there. It's log base 10. But the thing, but the implication here is this function, its domain is going to be the same as the range of the corresponding inverse function. And the inverse function would be 10 to the x, right? These are inverse functions, log of x and 10 to the x. Its domain, again, is all real numbers, like the one up here, but its range is everything greater than 0, right? Everything greater than 0. And so here, the logarithmic functions, the values of x have to be greater than 0. Greater than 0. Okay, so I can't take the logarithm of 0 because there's no value, no exponent, right? Remember, the logarithms are the exponents. There's no exponent on 10 that will give me 0. Okay, 10 to what power? If I say 10 to what power equals 0, well, you're not going to get a real number answer to that, right? Again, it's not 0 because, 10 to the 0 power, just like 3 to the 0 would be 1. 10 to the 0 is 1, right? So it's not 0 power. There is no power, right? In fact, the domain for any exponential function is everything greater than 0, right? So we can't have take the logarithm of any value that is 0 or, of course, negative. So the bottom line is whenever you're taking, finding the domain of a logarithmic function, here's a logarithmic function. F of x is the natural log, right? Remember, ln is base e. ln is log base e, but we write as ln. But same thing, this stuff here has to be greater than 0. So you simply do 3x plus 7 must be greater than 0. Okay, so very similar to what we had when we were looking at the square root. We had to have what under the radical greater than or equal to 0. But for the log functions, the input must be greater than 0, not greater than or equal to, but greater than 0. Solve this is a linear inequality. Subtract 7 from both sides, and then divide by 3. So x is greater than negative 7/3. Don't include negative 7/3. There's the domain, everything greater than negative 7/3. So same thing here, another logarithmic function, again, base e. Here's the input. So we simply are going to take that input and we're going to make it greater than 0. Okay. Now, this is an inequality that is not linear. So we've seen some linear inequalities, which we just isolate the value of x, right? Just like we would a linear equation, but that's not how we do nonlinear equalities. Remember what we have to do here. We have to factor this. Notice we have it 0 over here. That's important. If we don't have 0 over here, we want to subtract or add, get everything over to this side so we have just 0 here. And then once it's set equals 0, we want to know when is this expression equal to 0 or undefined. Of course, this is a polynomial function, so it's never going to be undefined, but it is going to be 0. In fact, you should notice right away that this thing factors as x plus 4 times x minus 3. And so this thing is equal to 0 when x is what? Negative 4 and 3. So what I like to do, and what you should have been done is, or shown how to do in pre-calculus, is do a sign check. I just do it this way. You can do a table of values. I just do it right above. Notice at negative 4 and 3, I'm going to write the sign of this polynomial, which is x squared plus x minus 12. It's 0 here and here, but in between, the sign is either always positive or always negative, because these are the only places where it's 0. Polynomial functions are going to be either positive or negative. So I plug in a value of x between negative 4 and 3, like 0, right? If I plug in 0 into here, what do I get? 0 squared plus 0 minus 12, I get negative 12. It's negative. So I just put a negative in between here to indicate that. So I'm checking the value of 0 here, any number in between negative 4 and 3. Pick a number bigger than 3, like 4. If I plug in 4, I get 4 squared is 16, plus 4 is 20. 20 minus 12 is positive 8. So I get a positive here. So anything greater than 3, the output will be positive. And then anything less than negative 4, like negative 5, squaring negative 5 gives me 25, plus a negative 5 is 20. 20 minus 12 is again 8, positive again. So here's the sign of that polynomial. And what do we want that polynomial to be? Greater than 0. It's greater than 0 when we're less than negative 4. And when we're greater than 3. And there's the domain. Okay. So again, nonlinear equalities have to be done this way with some sort of sign check so you see what's going on. Of course, most of you probably recognize x squared plus x minus 12 is just a quadratic function. The graph is a parabola. And if I were to graph this function, it would look like that, right? So we're simply saying it's below the x-axis, negative between negative 4 and 3, above the x-axis for values less than negative 4 and greater than 3. And those are the values we want to give us a real output. In other words, if I plug in any number between negative 4 and 3 into this function, I'm not going to get a real number output. Trig functions also, you need to know the domain of. Sine and cosine, you should know the domain is all real numbers. Okay, sine and cosine, no problems. Their domain is all real numbers. The problems are tangent, cotangent, secant, and cosecant. So tangent x is equal to sine of x divided by cosine of x. So now you're going to need to know, when is cosine of x equal to 0? If I think about the unit circle, if you're thinking about the unit circle, where is the cosine going to be 0? When the x coordinate is 0, it's going to be up here at pi over 2 or down here at 3 pi over 2 on the interval from 0 to 2 pi. But again, the function's domain, if we go add what? Pi or subtract pi, we're going to be down here, right? Pi over 2 plus pi is 3 pi over 2. Add pi more, I'll be at what? I'll be at 5 pi over 2. And I can just keep adding pi or subtracting pi, and I'll be at a point where cosine is 0. We need to exclude those values. So that we want to have x not equal to pi over 2 plus any multiple of pi. And typically, when we say multiple, integer multiple, I'll use n for that, where n is any integer. So that's one way you can write the domain. So the set of all x such that x is not equal to pi over 2 plus n times pi. And there's really infinitely many locations where the tangent function is not defined. If you remember, the graph of the tangent function has vertical asymptotes at those locations. Okay, so its domain would be everything except those infinitely many points. Okay, secant, cosecant, cotangent, similar arguments there. Okay, just some quirky ones, a couple quirky ones to close. What is the domain of this function? Square root, we see everything under the radical, which I have graciously factored for you, must be greater than or equal to 0. Remember that, greater than or equal to. And now I'm going to do the same thing. This is not a linear inequality. It's nonlinear. It's completely factored. And I know that this polynomial is equal to 0 when x is 0, when x is 4, and when x is -2. So I'm just going to put zeros above those. I know the polynomial is 0 there. And then I'm going to check the intervals, plug in something less than -2, like -3. Well, if I square -3, that's going to be positive. -3 minus 4, that's a -7. -3 plus 2, that's a negative. When I multiply a positive times a negative times a negative, since there's an even number of negatives, it's going to be positive. Okay. Or you can just use your calculator and plug in any value of x less than -2 into this, and all I'm interested in, what is the sign, S-I-G-N, of that. Between -2 and 0, I plug in -1. That's going to be positive again. -1 minus 4 is negative. -1 plus 2 is now positive, right? So a positive times negative by a positive is negative. And then I check between 0 and 4, like 1. If I plug in 1, 1 squared is positive. 1 minus 4 is negative, -3. 1 plus 2 is 3, positive. Again, positive, negative, positive, it's negative again. And then something bigger than 4, like 5, positive. 5 minus 4 now is +1. 5 plus 2 is +7, positive times positive times positive, positive. So I'm just checking the sign of what's under the radical. And here is the conclusion to that. And we're looking for what? When it's greater than or equal to 0. So this time I'm going to include -2 and 4 because they're 0, and then anything less than -2 and anything greater than 4. So there's the domain for this function. Last one, again, I've got a big fraction and a smaller fraction. Let's look at the smaller fraction first because I'm dividing 4 by what? X plus 1. So I know x plus 1 cannot be equal to what? 0, because I have division by 0, which means x cannot be equal to -1. So we know that. Also, 4 divided by x plus 1 minus 7, that cannot be 0, right? Because this whole thing is 0. We're dividing 3 by 0. That's undefined. Okay, well, that means that 4 divided by x plus 1 cannot equal what? Adding 7 cannot equal 7. Otherwise, that difference would be 0. And then here, how's this going to work? What do I need x plus 1 to be so that when I divide into 4, I get 7? Okay, so in other words, I want to actually solve this equation. 4 divided by x plus 1 equals 7. I want to solve that equation, because when I get that value of x, that's what I want to exclude here. Okay, so how do you solve this type of equation? What do? Well, just multiply both sides by x plus 1. All right. Just a linear equation now. Distribute my 7 through. So I get 4 equals 7x plus 7. Subtract 7. 4 minus 7 is negative 3. And then dividing by 7, x is negative 3/7. And so this is exactly what I do not want x to be, because then this expression 4 divided by x plus 1 minus 7 would be equal to 0, and I'd have division by 0. So the domain, I can't have those values, so my domain in conclusion would be the set of all values of x such that x is not equal to -1 or -3/7. Okay. So hopefully that's sort of a review. Some of it should be familiar to you. There is some links in the prerequisite review material if you need to algebra and trigonometry review from, I think, Khan Academy, for instance, and they have more examples there as well. Okay, I hope this helps kind of clarify the domain issue. In particular, in calculus, a lot of times we're interested in where a function is continuous, and of course that for most of our functions is simply on their domain for most functions. Okay.